Today's experiment we will be exploring the common ion effect using the equilibrium, the solubility equilibrium of calcium hydroxide as it dissolves into a solution. So we know that for a solubility product equilibrium, that the KSP, the equilibrium constant that governs this reaction, can be calculated in a normal way. We take products over reactants, but the reactant this time is a solid. So the KSP expression for this reaction would be the calcium concentration in the solution total, no matter the source, and the hydroxide concentration squared, the total amount no matter the source. Now, if we are in pure water, we would see that the calcium ion concentration would be expressed as X, and the hydroxide ion concentration would be expressed as 2X. But if we're not in pure water and there's an outside source of a common ion, we would see a different occurrence here. This is known as the common ion effect, where if we have an outside source of hydroxide, so say we try to dissolve calcium hydroxide in a solution that already contains some dissolved sodium hydroxide in it, the additional hydroxide that's present initially by Le Chatelier's principle will drive this reaction to the left. So we'll still have to fill in, if you look at the ice table, we'll still have to fill in some X and some 2X from the equilibrium itself, but the amount of X will diminish because the reaction is going to shift to the left and it's going to diminish the solubility of the calcium hydroxide. So that's the common ion effect. What we're going to do is we're going to go ahead and investigate the common ion effect by calculating the KSP at various concentrations of hydroxide. We should see that the KSP stays constant because the law of mass action states that the KSP is constant. So remember that the KSP has to be the total calcium concentration and the total hydroxide concentration squared. So what we're really interested in is the effect here on X. If the equilibrium is shifted to the left, the amount of calcium generated by the dissolving of the calcium hydroxide should go down. So how are we going to determine that? Well, if you see that in this balanced chemical reaction, whenever we get X amount of calcium, we're going to produce 2X amount of hydroxide. It's going to be twice the amount of hydroxide. So if we measure the amount of hydroxide produced by the dissolving of the calcium hydroxide, then we should know that the calcium concentration will equal 1/2 the hydroxide concentration, where the hydroxide is not the total hydroxide, but the hydroxide that's been provided from this solubility equilibrium. So same is true of the calcium. So the calcium produced by the equilibrium, X, is going to be half the hydroxide concentration produced by the equilibrium. That makes sense because the hydroxide is going to be 2X. So what we're going to do is we're going to go ahead and measure the hydroxide concentration total in a solution, and then from there we're going to determine how much hydroxide is produced. I'll show you that shortly, how we're going to determine how much hydroxide actually comes from the equilibrium and calculate the calcium. But for a moment, let's consider how we're going to measure the total hydroxide. So we know that hydroxide can react with a strong acid to produce water. This is simply a neutralization reaction. So that's what we're going to do. We're going to take a strong acid, in this case we're going to take hydrochloric acid, and we're going to react it with all of the hydroxide in a solution. So we'll try and dissolve up some calcium hydroxide. The solution can contain some extra hydroxide, and it will also produce some hydroxide by the equilibrium. Those two things will equal the total hydroxide. So the total amount of hydroxide will equal the hydroxide from the equilibrium plus the hydroxide that's provided from the solution itself, the outside common ion. Okay, when we neutralize it with hydrochloric acid, we're going to be measuring the total. Now, the hydrochloric acid we're going to use has this concentration here. So just to remember how we would calculate that then, if we used 10 milliliters of 0.0301 molar hydrochloric acid, and we use that to neutralize 10 milliliters of a solution that contains hydroxide, and the hydroxide is the only thing that reacts with the hydrochloric acid, we should be able to calculate the concentration of the hydroxide. So we know if we take the 10 milliliters of the substance that we know, we're going to use a burette, so we can use 2 decimal places here. Multiply that by the concentration of the hydrochloric acid using units. The concentration can be expressed in millimoles per milliliter. That allows me to not have to switch out of milliliters. That's going to equal the concentration of the sodium or the hydroxide ion that we're neutralizing, because it's a 1-to-1 reaction. We would get the total amount, that's going to be 0.301 millimoles of hydroxide that we've neutralized. And then to get the concentration of that hydroxide, again, this is going to be the total concentration, not just the concentration from the equilibrium. This will be whatever the hydrochloric acid finds in the solution. We would take the millimoles of hydroxide that we neutralized and divide it by the volume of the hydroxide that we neutralized. So if we neutralize 10 milliliters, we're going to use a pipette, so that's also good to 2 decimal places. We would see that the concentrations, of course, would be the same because we used equal volumes. It would be 0.0301 molar for the total hydroxide concentration. So that's how, using a neutralization reaction, that's how we're going to determine the total hydroxide concentration. But that doesn't tell us how we're going to determine then the resulting calcium concentration that went into the solution, because remember, the calcium concentration is not tied to the total hydroxide concentration, but only to the amount of hydroxide that was produced by this equilibrium reaction. So if there's an outside source of hydroxide, we have to take that into account. To perform our calculation then to determine how much calcium was provided by the equilibrium, we would have to organize our data table and understand how everything here is connecting in the data table. So let's say that the calculation that I just did was what I discovered. In run number 2, I discovered a total of 0.301 molar hydroxide ion was found in my solution. In run number 2, what was done was calcium hydroxide was dissolved into a solution that already contained 0.0158 molar hydroxide ion. So that's the hydroxide ion provided by the solution. Okay, the solution was already containing this amount. So how do I determine how much the hydroxide was provided by the equilibrium? So remember, the total comes from 2 sources. It comes from what's already in the solution. Again, the hydrochloric acid doesn't know where the hydroxide comes from. It just neutralizes whatever it sees in the solution. So it comes from the solution itself, and then it also comes from the equilibrium. To determine how much we got from the equilibrium, we would simply subtract. Subtracting the 0.0158 from the 0.0301 will give us the hydroxide that's provided by the equilibrium. So I'm going to subtract the solution from the total, and that should tell me how much calcium hydroxide basically dissolved. The number here will come out to be 0.0143 molar. Now, this came from the equilibrium. So we know the calcium we've already discussed will be provided at half the amount of the hydroxide. To get the calcium then, we would take and divide this number by 2 to get the calcium ion concentration. So we would take 0.0143 and divide that by 2. That gives me a calcium concentration of 0.00715 molar. At this point, probably better to use scientific notation, but anyway, that's what it is. Now, it's really important when you're doing the KSP to remember that you're going to take the calcium concentration times the hydroxide concentration squared, but this hydroxide has to be the total. The KSP doesn't care where the hydroxide comes from. It just knows that it has to manage the same number for whatever calcium ion concentration it finds in the solution and whatever hydroxide ion it finds in the solution. So to solve for the KSP in this example, we would take the calcium concentration and we would multiply it by the total hydroxide concentration, quantity squared. So that would give us 6.4, 6.5 times 10 to the minus 6. Now this is not meant to represent what you will see in terms of your data. Then your numbers might not match that at all. I just threw some numbers out there as a trial to show you how to do the calculation itself. So you'll fill in your own numbers, determining the hydroxide total, and then from there, knowing what our solution concentrations are, and these are the ones that you're going to see, and you should be able to determine the rest of the values and get the KSPs. In the end, you'll take the 4 KSPs and you will report an average of the 4 KSPs. Theoretically, they should be the same because we have to follow the law of mass action. What you should take special note of is the concentration of the calcium, because that's going to describe the solubility, because the calcium ion concentration always equals X.